Okay, so now we're looking at how the value of c affects the graph of this quadratic function when it's in standard form. So just as a review, we've already done just an ax squared, and now we're doing an ax squared plus c. Okay, that's still not completely everything because the quadratic function in standard form is ax squared plus bx plus c. So we haven't done the bx yet. That's what we're going to get to in just a little bit. And remember, all of that is a modification of this parent function of just the x squared. So x squared gets changed today by the a in front and adding the c in the back. What does that actually do to the graph? If you remember that when the a is going to either be a vertical stretch, which is going to bring it closer to the y-axis, or it's going to be a shrink, vertical shrink, which would have it go away from the y-axis. And then that's what the a would do. That's what the a does, is a stretch or shrink. But what does the c do? Well, that is a translation. It either would move it up or down. So we looked at each one separately, and so what's our goal today is to see what they do when you have both in the same one. In other words, when you have an a number in front, and you have a c, this number in back, okay? How does that affect this parent function, the x squared? Okay, how is that going to affect the parabola? How's that going to move it? How's that going to change it? And that's what we're going to look at today. So starting off, it says compare the graph 4x squared plus 1, or graph it, and then compare it to the graph of this f of x equals x squared, which is basically the parent function. How do you do that? Well, the steps are the same. Believe it or not, they haven't changed when it was just an a in front, or when it was just, we call this a k, by the way, a k at the end. It doesn't, the c value, it's called a k. It doesn't really change it at all. And we do the same steps. What's the first step? Right. So we're going to make a table, plot the points, and draw a curve through those points. So the first step is to make a table. So why don't we do that? So we have our x and then our g of x, with our x being our input, and then our g of x being our output. So let's go ahead and put some numbers in there and see what we get. Now, it's true that you can choose any numbers you like, but I like to stay consistent. So I'm going to go with a -2, -1, a 0, a 1, and a 2. These numbers are really nice because remember with the parent function, you end up with getting, when we did this one last class, you ended up getting numbers on both sides of the y-axis. So you can see when you do negative numbers for x that almost the reflection of it, you can see this mirror of it, if you will. It's symmetric. It's symmetric, both sides. Okay, let's go ahead and substitute these in then. So if I substitute a -2 into this equation, what do I get? So it's 4x squared plus 1. But instead of an x, I'm going to substitute in this first value of x, which is the -2. So what's great about this is even though it's a new thing, it's pretty easy because it's just the order of operations. Those please excuse my dear Aunt Sally. So the first thing you should do is work inside the parentheses. There is none. Then you should do exponents. So what is -2 to the second power? Well, that's what I should do first. I should do exponents first. So a -2 times a -2. Well, a negative times a negative is a positive, and 2 times 2 is 4. So these two I combine together to get a 4. I'll bring everything else down. So g of x, which was a 2. I should have wrote a 2 there. That's okay. So what should I do next? Well, after you do exponents, you should multiply or divide. So I will multiply. 4 times 4 is 16. Bring down the plus 1. So g of negative 2 equals 16 plus 1. 16 plus 1 is 17. So if I input a negative 2, my output will be 17. Okay, so we essentially do the same thing with all these numbers, right? We input a negative 1. Let's see if we could do it in our head. A negative 1 squared is a negative 1 times a negative 1, which is a positive 1. Then you multiply. 1 times 4 is 4. Then you add. 4 plus 1 is 5. If you input a 0, what do you have? Well, a 0 squared, remember you're doing the exponents first. A 0 squared is 0. That 0, then you multiply. 0 times 4 is still 0. But then you add or subtract, depending on which one's more to the left. So 0 plus 1 would be 1. Okay. Now earlier, everything we did mirrored numerically. Then you could see this pattern of if I put in a negative 2, I would get the same answer as if I put in positive 2. Let's see if that's also true. 2 times 2 is 4. 4 times 4 is 16. 16 plus 1 is 17. Well, that's true. Oh, I did the 2 first, sorry. Skipped. I should have done the 1 first. If that's true, what do you think is going to happen if I put a 1 in? Should it come out of 5? 1 squared is 1. 1 times 4 is 4. 4 plus 1 is 5. Yeah, so it works out. Sorry for the mistake there. And so we get this pattern, but then it says graph the pattern and then compare it to f of x equals x squared, or another way to say that is the parent function. Okay, so let's go ahead and do just that. We'll graph it and see how it comes out. Let me see if I have a graph here. I do. So as we're graphing this, I just want to keep some things in mind really quick. Let me see. Can you see both of these on my recorder? Yeah, all we need is this table, right? We're just doing those steps of writing the table, plotting the points, and drawing a line through them smoothly, right? These steps. Okay. So we made a table. Now we're plotting these points. If x is negative 2, y is 17. If x is negative 2, y is 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh man, this isn't quite fit. That's okay. If x is a negative 1, y is 5. 1, 2, 3, 4, 5. If x is 0, y is 1. If x is a 1, y is 2. Well, at this point, it should just be symmetric, right? So if x is a 1, y is 5, right? X is a 1, y is 5. If x is a 2, it's 17. Oh, let's see what happens when we smoothly connect these lines. I try to anticipate the angle a little bit, so it's not a abrupt connecting of the lines. Okay, so looking at this, it says graph, which we just did, we graphed it. And it says compare the graph f of x squared to this new graph. So we're going to compare it, okay? So let's go ahead and do that. And if you remember how we compared each one individually before, it should be helpful in comparing these because we're just combining those two ideas, okay? So how would we compare them? What would we say? Well, both graphs have the same axis of symmetry. If you are to divide this parent function in half, remember this is the parent function, right? I just had it on there before we started. If you were to divide it in half, So it's symmetric. You're also dividing this one in half. They have the same parent function, which is x equals 0. So I would say same axis of symmetry. Axis of symmetry. How else can we compare them? What else can we say about them? Which I'm going to put on there too, that it's x equals 0. Well, I would say the new graph is much narrower. So the new graph is narrower. What do we call this new graph? We're calling it g of x. So I'll say g of x is narrower. What about its vertex? Its vertex is not the same, right? The parent function vertex is 0, 0, but this vertex is 0 for x, but you're going up 1 for y. So I would say g of x vertex is 0, 1. Any other observations we can make? So it's a vertical stretch or shrinkage. If we started here and we're stretching towards the y-axis, we would say that it's a vertical stretch. And how much of a vertical stretch is it by? Well, we can look at this number in front. Remember, that's the same as the ax squared. And it's a vertical stretch by a factor of 4. I could just write the equation here, actually, so going back and forth. So it's a vertical stretch by a factor of 4. So g of x is a vertical stretch by a factor of 4. How did I know 4? Because that's the number that is in front of the x here. And then now there's one other category we can look at, and that's how much was it, not only was it stretched, but it also moved, right? And it moved, how many did it move to go from here? Just look at the origin here, the vertex. It went to here. So that moves upward how much? Right. So that would be a vertical translation 1 unit up. Upwards or up. Okay, that would be the answer, but I want to point out something, that it went up 1 unit, but you could have seen that from the question. See how it was a +1? Whatever the k value is. Right now we're thinking this is a c, I know, but we're going to call it k later. Start doing it now. Whatever the k value is how much it gets translated. So if k would have been +5, it would have gone up 3, 2, 3, 4, 5, it would have gone up 5. Right? If k were a -3, it would have gone down 1, 2, 3. So that's a good way to think of this last number. It just tells you whatever it says, that's how much you're moving the graph up or down. That's how much you're translating it.